Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in mathematics ranging from algebra through calculus and more advanced topics as well, please consider subscribing to our channel, checking out our videos, our playlists, liking, sharing, commenting. All those types of things are very helpful to us and help our channel out. Let's get into the current video. I want to take a look at equations of planes in space. Now, first and foremost, when I say space, what I'm referring to is three-dimensional space. What that looks like is the following. Okay, so I've got three coordinate systems here. I've got x, y, and z. And the idea is that the y and the z axis, or the yz plane, lies directly in the board, and the x axis, which I have as this line right here, is meant to actually stand perpendicular to the xzy plane, and so it's supposed to stick out of the board orthogonally to z and y. What I want to take a look at is how could we come up with the equation of a plane. Let's say here's a segment of the plane. Okay, so here's this segment of a plane. Of course, it continues in every direction. How could I come up with the equation of that? Now, if you think back to finding equations of lines, we need to start with two pieces of information. We need to know a point on the line and the slope, or 2 points, or something like that. But we need two pieces of information. Same thing here. What I need is a point in the plane, okay, that I'll abbreviate as P naught. So this point right here is P naught. And let's say P naught is given by the coordinates A, B, C. And then what we also need is a normal vector. Okay, a normal vector meaning that a vector that is orthogonal or normal to the plane, which I will label as the vector n. So n is a normal vector. Now, given those two pieces of information, we can determine whether or not a third point lies in the plane. Let's say I give you this point right here. And I'll label that as the point P. And down here, I'll say P has coordinates x, y, and z. Okay. Well, how can I determine? So again, here's what I know. I know the point P naught, I have its coordinates. I know the vector n, I have its components. I have those two pieces of information. From that, I want to determine if this arbitrary point P, or a point that I can test, so I can pick a specific point or use an arbitrary point, to determine if that's in the plane or not. Well, what I'm going to do is I'm going to consider, as I drop a marker here, I'm going to consider the vector that starts at P naught and ends at the point P. Okay? So I want to consider that vector right there, which would have notation would be P naught to P, and it'd be that directed vector. Well, the point P lies in the plane if and only if the vector that I just created, P naught to P, and the normal vector are orthogonal. So that means that P is a point in the plane if and only if P naught to P is orthogonal to the vector n. Well, we have a computational test to determine if two vectors are orthogonal. And so another way that I can write this is I can say that the point P is in the plane if and only if the following condition applies. If I take the dot product between those two vectors, I have to get 0. And this right here is the equation of the plane. Okay. Let's take a look at a handful of examples of finding equations in planes given various pieces of information. First example. Find the equation of the plane containing the point P naught, which is 2, 5, negative 1, and which is orthogonal to the vector n, or in other words, has normal vector n, which has components negative 1, 4, 3. So find the equation of the plane containing that specific point and which is orthogonal to, or said differently, has normal vector n, which has components negative 1, 4, and 3. Okay. So let's take a look at the solution. So for this first example, I'll leave my general sketch up there. Solution. Well, again, this right here is the equation of the plane, so this is essentially a test to determine whether or not a point lies in the plane. And so what I'll do is I'll start with the general equation, P naught to P dotted with the vector n is equal to 0. Okay. Now remember that the vector, the directed line segment, so the vector P naught to P, starts at P naught and ends at P. And if you remember, the way we come up with the components for a vector between 2 points is I subtract the components, starting with the ending points and subtracting points from the initial point. In other words, if P is the generic point x, y, z, then the vector from P naught to P would be x minus 2, y minus 5, z minus negative 1, okay, dot product with the vector n, which was negative 1, 4, and 3, and that's equal to 0. Okay, sorry, that's getting kind of squeezed in here. Let me separate that a little bit. Okay, so then just take the dot product. Okay, so when I go ahead and take this dot product, negative 1 times your first component would give you negative x plus 2. 4 times your y component would be plus 4y, and then 4 minus 5 would be minus 20, and then 3 times your z component would be plus 3z. Negative negative is positive, so it's positive 1. 1 times 3 would be plus 3 is equal to 0. And now let's clean that up. Well, there's no like terms for the x, y's, and z's, so I'll just record those first. So negative x plus 4y plus 3z is equal to, and then if I take all the constants, I've got 2 and 3, so there's 5, and then negative 20, that'd make that negative 15, and then if I add that to the other side, I'm going to get equal to 15. Okay. This right here then is the equation of the plane that passes through the point 2, 5, negative 1 and has normal vector negative 1, 4, 3. I'm going to make 2 additional comments on that equation for this example, but let me clean this spot up right here first. Okay, because one of these comments I'm going to make as a general note up here. Okay, first and foremost, if I take the original point, the 2, 5, negative 1, I could take that and plug it into this equation here, and I see that it's actually going to satisfy it. Okay, so that's one just quick test just to see, make sure that we have our example right. If I take that point, plug it in, and make sure that actually satisfies it. The other thing, and I'm going to make this a specific note here in a second, and if I take a look at the normal vector, negative 1, 4, 3, and if I go over to the equation of the plane, notice that the coefficients, negative 1, 4, 3, match the coefficients or the components of that normal vector. Therefore, if I give you the equation of a plane, we already know one vector that is normal to it if I just take the vector with components consisting of the coefficients of x, y, and z. Okay? Therefore, note for the equation of a plane ax plus by plus cz is equal to d, we know that n, which has components a, b, c, is normal to the plane. Okay. Therefore, if I have the equation of a plane, but I don't have a vector wasn't given, I can construct a vector by taking components consisting of the coefficients of x, y, z. And of course, anything that's parallel to this one would be normal as well, because if it's parallel to n, then it's also going to be normal to the same thing that n is normal to. Meaning, if I take the vector consisting of -2, 8, and 6, so I just take this and multiply by 2, that would be another normal vector. And one reason I say that is because, well, what happens if I can say reduce these? Like, let's say I have the vector that consists of 2, 4, 6, right? Just for easy example, then I could actually divide it by 2 and get 1, 2, 3, and just get a component with smaller numbers. And so that may or may not be a computational help at some point. But again, I can multiply through by a constant, non-zero constant. Okay. What I want to do is let's take a look at one more example, and let's kind of generalize, or not generalize, but sort of take a next step into the example that you looked at in your algebra class, where it says find the equation of the line passing through 2 points. Okay. Well, in this case, what we need is actually 3 points. So let's see what that looks like. If I give you 3 points, can we actually come up with the equation of the plane? Let's see how that would work. This definitely does not erase as fast as a whiteboard does, but it gets pretty good. It's okay. All right, let's take a look at the next example. Find the equation of the plane passing through so the following 3 points. A, which is 1, 1, -1. B, 0, 2, 1. And C, which is -1, 0, 2. Again, this is looking at the next dimensional case when we say find the equation of a line passing through 2 points, which is what you're familiar with in your algebra class. Now we're looking at find the equation of a plane passing through 3 points. Let's look at the solution for that. Okay. What do we need? Well, the equation of the plane, remember, was P naught to P, that vector dotted with n is equal to 0. P naught is a fixed point in the plane. N is going to be a vector that is normal to the plane. And P was just the generic point x, y, z. That's how I get my variables in there. So how do I come up with that? Well, P naught, again, is a fixed point. So I can really label that as A, B, or C. Makes no difference. I will, in this case, I'll say the point P is A, which is 1, 1, negative 1. I know that that point lies in the plane. Well, let's see. Let's do a sketch here and see if we can figure out how we could come up with our normal vector. Once again, let me do a sort of a generic equation or sketch of a plane here. And let's plot 3 points. Okay? Let's say I've got, let me see if I can do a different color. Maybe this will stand out better. Let's say I've got this point here, which is the point A. I've got this point here that I'll label as B. And then I've got this point here that I'll label as C. Well, between a pair of points, I can come up with a vector. So first and foremost, I need a vector n. I have to somehow come up with a vector. Well, I can come up with a handful of vectors using A, B, and C by just taking the vectors that start at one point and ending at another. So in particular, I could get the vector A to B, okay? And what do I know about the vector A to B? Well, I know that the vector A to B lies in the plane, okay? We also know that the vector from B to C lies in the plane. How could I then take those two vectors, the AB vector, the BC vector, which both lie in the plane, and somehow construct a third vector that would be n, which would be our normal vector? Well, if you remember our different operations between vectors, of course we can add them and scalar multiples and those types of things, but as far as multiplication, we know that the dot product is a test for determining whether or not two vectors are orthogonal, but that doesn't construct an orthogonal vector. Notice that the dot product gives me a scalar. In other words, the dot product has another term, the scalar product. Well, the cross product is what we're going to use here. And actually, if I say that's the vector AB cross BC, remember that the cross product of two vectors is orthogonal to both. If it's orthogonal to both, it's orthogonal to the plane. Therefore, this is going to be my normal vector n. N is the cross product between AB and BC. And then how do we compute a cross product? Well, remember, a cross product between two vectors is a determinant where the first row of the determinant consists of the unit vectors I, j, k. The second component, or the second line of the determinant, consists of the components of the first vector, which would be A to B. Now, over here, let's see, what are the components for A to B? Okay, we talked about this a moment ago. Remember, when I have a vector consisting of the directed line segment from A to B, the components consist of the difference of the points from B to A. Therefore, it would be 0 minus 1, which is negative 1, and then 2 minus 1, which is 1, and then 1 minus negative 1, which is 2. There's the components of the vector A to B, and that, again, is my second row in my determinant. Now, how about the vector B to C? Well, B to C, extend that out a little bit there, B to C is the components of C minus the components of B. Therefore, it would be minus 1 minus 0, which is minus 1, and then 0 minus 2, which would be minus 2, and then 2 minus 1, which would be 1. And those would be the components of the vector from B to C, and therefore would be the third row of our determinant. Negative 1, negative 2, and 1. Okay. Now let's expand that determinant. Expanding along the first row, remember that the way to evaluate a determinant, if I go along the first row, is I take the first component of the first row, and then I multiply that by the determinant consisting of what would be left over if I were to delete the row and column that I is in. Therefore, the 2 by 2 determinant consisting of 1, 2, -2, and 1. The next one I would have is j times the determinant consisting of -1, 2, -1, and 1. And then I would have k times the 2 by 2 determinant consisting of -1, 1, -1, and -2. And the other thing to remember is that we alternate signs. If I expand on the first row, it's going to be plus, minus, plus. Therefore, I leave this as, I don't put a sign there, so I just leave it as plus. Then the second one would be minus, and the third one would be plus. Okay? Then I have I times what value? The way we evaluate a 2 by 2 determinant, we multiply the main diagonal, and then I subtract the off diagonal. Okay? For this first 2 by 2 determinant, 1 times 1 is 1 minus -4. So that'd be 5. Minus j times main diagonal would be -1. Off diagonal would be -2. So I have -1 plus 2, which would be 1, plus k times main diagonal will be +2 minus -1. 2 minus -1 would be 3, and that has components 5, -1, and 3. Therefore, that vector right there, 5, -1, 3, is orthogonal to the plane, and again, is my normal vector n. Okay? Now, at this point, I have the point P0, and I have a normal vector n, so this just turns back into the first problem that we did, and we proceed, of course, the same way. And I know I don't remember. I just made that example up off the top of my head. What did I use for my initial point? You know what? I don't remember what my initial point was. I have my vector n, but again, I would take the point P0 to P, dotted with the vector n is equal to 0, and then we would put x minus blank, y minus blank, z minus blank, dotted with the vector n, which is 5, -1, 3, equal to 0, and proceed like the previous example, and I don't remember what the point was that we picked. Okay, but it's the same thing as the previous example. All right, hope you learned something from this video and figured out a way to find equations of planes in space. Thank you for watching, and please consider subscribing.